All right. So welcome to the morning of the fourth day of the workshop. I'm delighted to introduce our first speaker of the morning, Matt Thorpe, who is will be talking to us from Manchester or nearby Manchester, and his topic is linearized optimal transport.
Thanks so much, Dan. So actually, I'm in Cambridge at the moment. I'm actually at the INI, but I guess relatively speaking, I'm much closer to Manchester than to Berkeley. Yeah, so I guess start off, thank you very much for the kind introduction. It's really nice to be able to participate in this workshop. I'm sorry I can't be there in person. I'd have really liked to have come and visit, but I guess it just wasn't really possible. Okay, so I'm going to tell you about some work I did with two of Katie's excellent students, Tanji and Junji, and Bernard Schmidt's. Oh, actually, sorry, his affiliation is out of date. He's at Göttingen now. Okay. Okay, so I guess to this audience, I don't really need to motivate the Wasserstein distance. I guess we all probably already think it's great. It's got nice sort of well understood properties. So theoretically, it has this sort of Lagrangian viewpoint, which is often much more reasonable for modeling than compared to the Eulerian viewpoint. But I think we probably also all agree that there are some sort of drawbacks. Okay, so particularly it's quite restrictive on the input. So we had to treat images or signals as probability measures. It's computationally quite expensive. And of course, we don't really have sort of off-the-shelf data analysis tools. So for example, if you wanted to do something like PCA or LDA, I wouldn't really know how to do this in the Wasserstein space. But of course, for the Euclidean space, it's just, I don't even have to think about it. I can just use an inbuilt function from MATLAB and everything works. Okay, so the object of this talk is to talk about a unbalanced optimal transport metric, which somehow relaxes the assumptions we're going to place on the sort of inputs. And then we're going to linearize this, and this kind of allows us to apply off-the-shelf data analysis tools, and we'll also make it computationally much more feasible. Okay, so I'll just start off maybe just a set notation, talking about the usual sort of Wasserstein distance. So of course, we probably all know that there's three different ways to define the Wasserstein distance. So let's start off with the Monge formulation, where we look for these optimal transport maps. We have the Kantorovich formulation, where we look for these optimal transport plans. And then finally, we have the Benamou-Brenier formulation, where we're looking at minimizing the kinetic energy of a fluid. Okay, so I'll be fairly relaxed about the assumptions, but under sort of fairly reasonable assumptions, all these three formulations are equivalent, so I can sort of go between them as I like. Okay, so if I sort of start off by sort of manipulating the Benamou-Brenier formulation, I can sort of write this down. Okay, just as the kinetic energy of this fluid at every sort of time step. Okay, I can also sort of recall that if I want to have a geodesic between two measures mu and nu, this is just given by pushing forward mu by this map T star T, where T star T is just a convex combination of the optimal transport map between mu and nu and the identity. Okay, I can also recall that along the geodesics, if I fix a particle and then look at how this particle moves, in this viewpoint, the velocity is constant, right? So this just means that my velocity of the particle my velocity along the trajectory given by T star T, right, this is just going to be equal to where I end up minus where I started from. And what this means is that I can look at this Benamou-Brenier formulation, and this time integral effectively disappears. So what I have is the kinetic energy at each time is equal to the kinetic energy at the start. Okay, so this is nice because we can now write this Wasserstein distance as just being the L2 norm of the velocity. Okay, so this kind of gives us the sort of formal Riemannian structure where we have, this the Wasserstein distance is just given by this sort of this inner product. Okay, so you can sort of take advantage of this and define the logarithmic map of the measure nu at the sort of point in the manifold mu as just being the velocity field. Okay, so from the previous slide, right, this means we can write the Wasserstein distance as just being the L2 norm of the logarithmic map. Okay, so this was kind of exploited by Diane and some of his collaborators, and they defined the linear Wasserstein distance as just being the L2 norm between the logarithmic maps. Okay, so what they do is they fix a reference point mu, and then they define the linear Wasserstein distance between mu1 and mu2 as just being the logarithmic maps okay, at the point mu of mu1 minus logarithmic map of mu2 at the point mu in the L2 norm. So this picture here is just kind of demonstrating what's going on. So what we would, so this is our reference point here, mu. Sorry for the change of notation between the figure and the rest of the slide. Because, okay, so the Wasserstein distance is this sort of red curve here, and then in the tangent manifold, this red line here is exactly the same length as the red curve, and similarly the blue curve here is exactly the same length as the blue curve here. And then the approximation, which Dan and his collaborators made, is that the green curve here, which is exactly the Wasserstein distance between mu2 and mu1, is approximately equal to the distance in the tangent manifold, which is this green line right here. Okay, so if we define this sort of linear embedding map, which is being the logarithmic map, right, we now have a way of sort of approximating the Wasserstein distance as a Euclidean norm. Okay. Yeah, sure, please.
Go ahead.
Just a very naive question. Could you please go back?
So I can't really hear. Can someone pass the microphone?
Yes. Right.
Okay, so yeah, very naive question. So when you define that linear Wasserstein distance, you minimize over mu.
No, so actually we just fix a reference point. So this can be, I mean, this could be anything. So of course, the best possible reference point.
Okay, I see.
Would be the Barycentres.
I see the point. Sorry. There's a subscript in mu. Thank you so much.
Yeah, no problem. Okay, so this slide is just kind of summarizing essentially what I said before, but also kind of saying how we actually kind of solve this problem, in practice. So I mean, there's a lot of sort of attention that has gone into this sort of synchron algorithm, which allows us to solve the Kantorovich problem fairly efficiently. So one starts off by finding these sort of optimal transport plans. Okay, via something like the synchron algorithm. From this, we can extract the optimal transport maps and doing something like barycentric projection. Once we have the maps, we can define the velocity vectors just being the map minus the identity. Okay, and so this gives us kind of the roadmap of going from a measure nu into the tangent plane. Okay, so this example is taken out of one of Diane's papers. It's just kind of to demonstrate, that we can still apply off-the-shelf data analysis tools. So they considered, well, at least two examples. So the first one is these sort of sets of cell images. So they carry out this framework, they work out what the tangent vectors are, okay, use this embedding into the linear optimal transport space, and then they can do things like principal component analysis. So I think this actually is really quite a nice example, because you can really sort of see here what the modes of variation in these images are. So for example, if we look at the top row, so this corresponds to the principal components, we can kind of see that if you look on the left-hand side, if you look on the right-hand side, well, we have something that's quite big on the left and something quite small on the right. And maybe the third line is also quite interesting, that we see the kind of the extreme, so this would be the third principal component. We see mass is really concentrated in the middle compared to mass being concentrated on the outside. Okay, and there's similar sort of things, in faces. Okay, this sort of framework also allows for data points to be generated. So the idea here now is that we start off by approximating this Wasserstein manifold at k different points. Okay, so let me just 2, 3. So, okay, so we have like a set of images. So mu I. We want to cluster these into K groups. So actually we did this by linearizing at one reference point, and then we just did K means. This then gives us cluster centers. So we call the cluster centers nu K, and these are the points which we're going to approximate the sort of Wasserstein manifold at. Okay, so at each of these K centers, we again use the linear optimal transport setting, but now we just use the images which we're associating to that cluster. Okay, and then we fit like a Gaussian model, so we find the mean and we find the covariance. Okay, so we essentially we pick a point. Okay, then we approximate this sort of tangent manifold with a Gaussian. Okay, and this now means that we have a distribution which we can sort of draw from. So if we wanted to generate a new image, we would sample one of the points, and then we would sample a tangent vector in that tangent plane. Okay, and then we can create a new image just by pushing forwards, well, just by defining the transport map to be the velocity vector plus the identity. Okay, and this seemed to work quite well in different applications. So I think one thing one can always ask in these sort of data generating examples is, are you really learning new images, or are you just sort of getting back what you put in? So we did this on like a very, very small data set. So we just took 19 images. So that the 19 images we took are on the top row, and then we generated sort of new images. And given that we only had 19 images, I think we did kind of a fairly reasonable job. So you can sort of see that none of these new images are exactly like one of the old images. I mean, it's not perfect. You can kind of see sometimes the mouse gets a bit sort of messed up, but it does a fairly nice job. Okay, so far this has all been on the balanced optimal transport. I've said nothing about unbalanced optimal transport. Okay, so to sort of talk about this, let's go back to the continuity equation. Okay, so this is in the Benamou-Brenier formulation. We were minimizing the fluids subject to satisfying the continuity equation. So a natural way to allow for unbalanced measures is to add a source or sink term. Okay, so we define the continuity equation with source as just being, we have our density rho, our momentum omega, and now we have this zeta, which allows for mass to be created and destroyed. The question now is, well, of course, we have to penalize zeta in some ways. Otherwise, you would never do any transport. You would just do creation and destruction. So how, what's kind of the right way to add the source term? Okay, so perhaps there isn't a right way, but there's maybe some ways that are more natural than others. So this was proposed by several groups. So Leonard actually spoke about this on Tuesday. So he's one of the groups that kind of proposed this sort of all independently. But this was also proposed more or less at the same time by Jacques Perrier, Schmitzer-Beilard, and Liero, Melke, and Savary. So the dates here, I think, correspond to when the papers were published. Actually, all these papers kind of came out, I think, within like 2 or 3 months of each other. Okay, so they proposed using the cost function of this form here, which is related to like the Fisher-Rao distance. Okay, of course, I mean, there's other ways. I think like Stanley Osher and his group, they use like an L1 penalty on zeta, and numerically, this is kind of a nice thing to do as well. It doesn't quite have the same geodesic structures, which one gets when they use a penalty of this form here, though. Okay, so this is the model which we're going to use. So we define the Hellinger-Kantorovich distance as just being the minimization over all the continuity equations with source of, so here we have kind of the Wasserstein part, then here we have this creation and destruction. And so for convenience, I put a factor of a quarter here. Actually, in some of the numerics I show later, this quarter is going to become a parameter lambda. And essentially, it will control the length scale over which we decide we either want to transport or if we want to do creation and destruction. Okay, so from now on, I'll sort of talk about this Hellinger-Kantorovich distance. And the question is, can we have the same sort of framework? So can we do this linearization? Yeah, and how does that work? Okay, so we kind of started off with the Benamou-Brenier formulation of the Hellinger-Kantorovich distance. So the question now is, well, is there a Kantorovich form? And actually, yes, there is a Kantorovich form. In fact, there are actually two Kantorovich forms. So I think I will just talk about one of them here. So let me start off by defining the Kullback-Leibler divergence in the usual way. Okay, I'll define this sort of cost function, which is now, okay, it's maybe a little bit strange compared to just like the Wasserstein cost function, which would just be x minus y squared. Now I kind of, x minus log of cos squared of x minus y. And this is only when x minus y is less than pi over 2. So this, so you can see immediately like we have like a threshold on how far we're going to transport. So if I want to transport from x to y, and x and y are further than pi over 2 apart, then of course I'm going to pay an infinite cost. So I can kind of see that my transport is limited. And this pi over 2, of course, right, comes from, would change if you change the factor here. Okay, so one can show that this sort of Benamou-Brenier formulation is equivalent to this soft marginal Kantorovich problem. So again, so in the sort of Wasserstein distance, one would normally just have the integral over the cost function, okay, where the cost function would be the quadratic norm. And then instead of penalizing constraints, one would say the marginals have to be exactly, mu and exactly nu. So here, P1 of push forward pi, this is the first marginal pi, and okay, P2 push forward pi is the second marginal. So now, of course, we're saying that the margins don't have to agree exactly, they just have to be kind of, approximately, close to mu and nu, where this sort of approximation is measured in terms of the Kullback-Leibler divergence. Okay, and so the minimization here is over all measures, all positive measures, not necessarily probability measures. And likewise, there's no assumption that mu and nu are probability measures either. They can be any sort of positive measures. Okay, a lot of the nice properties of the Wasserstein distance all sort of carry through. So one can show actually this infimum is actually a minimization, is a minimum. Okay, and one can show further that the optimal pi star is supported on the graph of a transport map. Okay, so but this time the first marginal is not going to exactly be mu. So in the Wasserstein case, again, one gets to identity cross T star, push forward of mu. Now we have this mu tilde. So the mu tilde is the first marginal of pi star. And this isn't going to be exactly equal to mu, but again, it should be kind of close because we're penalizing this marginal in the Kullback-Leibler divergence. Right, okay, so I put kind of a warning here because there's some kind of terrible equations on the next slide, which, at least for me, these aren't really very informative. I wanted to show them just to kind of say, okay, we do have equations, right? We can kind of write these sorts of things down, even though I think you can't really, well, at least I don't look at them and they don't seem particularly natural to me. Although there is actually quite a nice sort of way of understanding these, but this would take a little bit of time to kind of explain where they're coming from. Okay. So what we have is we have our inputs, mu and nu, which are just positive measures. Okay, we'll have some pi star, which is optimal. So again, we can kind of use something like the sinkhorn algorithm. This will solve our soft marginal Kantorovich problem. Okay, then from that we have to extract our optimal sort of Monge map T star. Okay, and then I'll let my nu tilde be the first marginal and nu tilde be the second marginal. What I can do now then is I can decompose the original measure mu into the part, okay, which is absolutely continuous with respect to mu tilde and this singular part here. So approximately I can sort of understand this as being this mu tilde is going to correspond to the transport part, and this mu perp is going to correspond to the mass that's completely destroyed. Okay, and similarly, my target measure nu, I can decompose this into something that's absolutely continuous with respect to my second marginal, and something that's singular. So again, this part here, the nu tilde part, this corresponds to the transport that's arriving from mu, and this new perp, this corresponds to mass that's going to be created from nothing. Okay, in that case, one can write down the geodesics. So we have this rho tilde. So the rho tilde is the mass that's transported from mu to nu. So this, of course, right, is a push forward of a measure with respect to mu tilde. Okay, so this capital M here is somehow the mass along the geodesic, and this x is kind of the trajectory. So the trajectory is a straight line. So it's just an interpolation between, okay, if we're moving from x0 to x1, then it's, we move in a straight line, but we don't move at constant speed. So the speed itself depends on some phi, which is given in this form here. And likewise, the mass along the transport, this again is, well, you can see here, it's essentially quadratic between, okay, so we're moving mass m0 from x0 to mass m1 at x1. Okay, then it's of this form here. Okay, so this anyway corresponds to how the density sort of evolves along the transport, and then we have the density that corresponds to the pure destruction and to pure creation here. So again, I mean, these are kind of just these are probably just special cases actually of rho tilde, but when, okay, so if m1 is equal to 0, okay, we get just this term here. Okay, so you can see our mass so is quadratically increasing. Okay, so the momentum, so of course momentum is only going to be defined over the transport. Okay, and again it takes this form here. And the creation of mass, again, we can break this into two terms here. So we have the creation and destruction along the transport, and then we have the pure, so this would be the pure destruction and the pure creation. Okay, so it's kind of important to know, right, that we have pure creation and destruction, and we have transport with creation and destruction. We don't have pure transport. Okay, so it'd be kind of nice. So in the Wasserstein case, what we could kind of do is say, well, let's just consider when time t is equal to 0. So we can already say that isn't going to work. And that's because this part here, the part where we have pure creation, this is going to be singular with respect to the measure that we started out with. So we know we kind of can't get, this sort of linear embedding in the same way as before. Okay, nonetheless, we can kind of do something. So, okay, so like before, I'll set velocity. Okay, it's just the momentum over mass. And then I have this term here, alpha, which this corresponds to mass being, okay, so it corresponds to the mass being created and destroyed along the transport. And we've included the pure destruction. So there's no pure creation here. And what we can, okay, so first of all, we can evaluate these formulas fairly easily when t is equal to 0. They're just given like this. So of course, where we're not transporting anything, the velocity is 0. Yeah, and then we have this velocity here where we are transporting, and mass creation and destruction. So again, if we have a pure, so this would be pure destruction, then this alpha naught is just -2, and okay, it takes a slightly more complicated form when we're transporting as well. Okay, but if we sort of we can rewrite the Hellinger-Kantorovich distance now in terms of something which only depends on a time t equals 0 plus this, I guess, this kind of annoying part, which is the pure creation. Okay, so this is almost exactly what we want. So we have a quadratic sort of L2 term, and then this annoying sort of total variation part. But we can also kind of get rid of this a little bit. So essentially, if we assume that our measure mu is kind of covers enough of the space, then what we have is that the pure the pure creation part is going to be 0. Essentially, so we can't do pure creation if we already have something there. And actually, we don't even need to have something there. We just need to have something kind of close enough to it. Okay, so if we assume that the support of mu is the whole space, then we have exactly the Hellinger-Kantorovich distance is given sort of L2 form. Okay, so this now allows us to kind of go back and to can essentially carry out the same framework that Dan did in his work. So we define the logarithmic map to be the initial velocity, and this alpha, which corresponds to the creation instruction. Okay, and then of course we can write the Hellinger-Kantorovich distance just being the L2 norm of the of this sort of now it's a very formal logarithmic map, because of course we're ignoring the new perp term. Okay, so we can define the linear distance as just being the difference between the logarithmic maps in the L2 norm. Okay, and the embedding map as being this logarithmic map. Okay, and we make the same assumption, right? That the Hellinger-Kantorovich distance between 2 points mu1 and mu2, this should kind of approximately be equal to the distance in the L2 norm between the two projections. Okay, and the roadmap is very similar to the previous map. So we start off by finding the optimal transport plans pi star. Okay, so we use the synchron algorithm for this. We can then extract the optimal Morge maps. And we have to find these, the densities U and W, which are the densities with respect to the marginals, mu tilde and nu tilde. Okay, we evaluate the velocity maps and this alpha term using the formulas in the previous theorem. Okay, and this all gives us a way to go from an arbitrary positive measure to our velocity and mass destruction and creation. Okay, so I think the rest of the talk now is just kind of some examples. So we did this on a very toy problem. So we have a data set which varies in two different ways. So one of the ways it varies, so the data set consists of two ellipses. So each data point is an image which contains two ellipses. So the yellow kind of indicates where there's mass, and everywhere, I'm not sure what color you would call the background, I think it's like blue or purple. This is where there's no mass. So the ellipses are kind of either on the sides, or they're sort of rotated round. And the other way that that these images vary is the amount of mass is different. So that actually isn't quite so clear in this figure, but I think on this side here, there's more mass in the top one and less mass in the bottom, and then it becomes more less mass here and more mass here. Right, so if we do these projections in the, okay, so first we do the projections in the Wasserstein space. I mean, we still get these sort of natural sort of clusters, but they're kind of more, I guess, sporadic. So here, I can't remember now what these, so I think these lines here indicate that the images, these images have the same amount of mass. So each X here corresponds to one image. We've done the linear embedding in the Wasserstein space, and then we just projected onto the two principal components. And then we've connected all the points which have the same mass. Okay, and they are actually kind of clustered together. If we do this in the Hellinger-Kantorovich space, somehow I think this is kind of gives us maybe a nicer picture, because now the variations in both space are kind of much, well, everything's much more uniform. So I think if we sort of look maybe at the columns here, like this is going to correspond to the elongations, and we can kind of see that changing the mass and changing the elongation is kind of gives us the same sort of the same sort of, I guess, clustering. Whereas here, if we change the elongation, we're going to jump to completely different part of our PCA space. And this is maybe more sort of evident when we sort of look at the velocity fields. So in the Wasserstein distance, you can see here that we end up having mass moving from one of the ellipses to the other ellipse. So here I think we have less mass, here we have more mass, so the mass is moving from the top to the bottom. We kind of see the same thing actually in both of the Wasserstein modes. So you can see here we still have mass moving between the two ellipses. Which is perhaps not as sort of physically not as nice. In terms of the Hellinger-Kantorovich distance, right, we get a really nice separation. So first of all, there's no mass moving between the two ellipses. And secondly, we can see that the first sort of principal component mode, this really corresponds to the top ellipse being sort of stretched out and the bottom ellipse kind of being pushed together. Okay, and in the second mode, this corresponds to the top, to the first ellipse being sort of shrunk, and then the second ellipse sort of growing, which are exactly the two variations that we put into this data set. Okay, so a slightly more realistic example is this sort of jet tagging case. So the data actually was simulated, but it's kind of simulated to kind of closely represent what one would still observe in sort of particle detectors, like like the one at CERN, for example. So here we kind of, at least my understanding is that we sort of imagine these images as being sort of like a plate, and then we're looking at where particles hit this plate. This kind of gives like a signature, and the question is, okay, what reaction does that signature come from? So in particular, we're looking at two different types. So these sort of W boson jets, and I guess this is QCD jets. Yeah. So okay. So I've plotted here some sort of examples of what we sort of see. So the QCD jets are in green. So these, I think, tend to be sort of like a singular particle surrounded by sort of smaller particles, whereas the W boson jets, these tend to be sort of two particles, but still surrounded by lots of sort of smaller particles. Okay, so kind of represent these as images. We can carry out our sort of linear embedding framework, and okay, we can sort of apply sort of off-the-shelf sort of data analysis tools. So here we've kind of plotted the Wasserstein distance when we so this is the Wasserstein embedding when we project onto the LDA axes. You can kind of see we don't really get to the great separation between, so the green here, so what was the green? So the green was the QCD jets, and the red was the other jets, the W boson jets, and we don't get a particularly great sort of separation in classes. Okay, so for the Hellinger-Kantorovich distance, we do better. So we plotted it here for a range of different scales. So if you recall, when I first introduced the Hellinger-Kantorovich distance, we had this factor of a quarter in front of the mass creation and mass destruction term. One can replace that quarter and put a kappa, and this kind of controls the length scale. So we kind of played around with the length scale a little bit, but essentially you can see that we do get, of course it's not perfect, there's overlap between the two sort of projections onto the LDA axes, but we do essentially do better. And actually, if we plot the first of the two principal components of the data, you can kind of see that we are getting a sort of, well, we're certainly not getting linear separation, but we are sort of getting separation. Well, things seem to be naturally sort of clustering together. You can kind of see that one sort of class sort of behaves like this, and then okay, most of our so I think this is the QCD jets, right, are sort of concentrated around here. It's also kind of interesting to note that where we kind of, I guess, do badly actually is kind of reasonable. So if we follow this sort of this trajectory here, we can sort of see, okay, so 1, 2, and 3, these are all the W boson jets, and yeah, we can sort of see, we have kind of two sort of, quite big particles surrounded by small particles. Then as we go into the into the green region, okay, we really have kind of one particle surrounded by small particles. Then over here, where they're technically, back to the, I forgot again what it's, to the W boson jets, actually, we still have like one particle here. So perhaps it's understandable that we're kind of getting this that we're separating these ones out. Okay, so of course, we did some sort of, off-the-shelf sort of labeling using LDA, KNN, and support vector machines. And the conclusions are, that the Hellinger-Kantorovich distance essentially, does the best. What sort of scale you want to use kind of depends on how you want to measure accuracy. So we looked at sort of area under the curve and this sort of true positive rate, false positive rate. Yeah, but the conclusions are that the best results are always sort of for the Hellinger-Kantorovich distance, and that's sort of scale between sort of well, I guess 0.5 and 0.1. Okay, so this is actually my talk is essentially done. So I have some sort of references. The papers that I kind of talked about mostly well, first of all, so this was the paper where we generated new data using the Wasserstein embedding, so the Wasserstein linearization. And then this second paper here, this is where we did the linearization of the Hellinger-Kantorovich distance and these applications to jet tagging. So, okay, so with that, thank you very much for your attention, and yeah, any questions?
Thanks, Matt. Questions? Yes,
yeah, so thank you for the beautiful talk, Matt. And so my question is, the linearized transport distance, the Wasserstein one, is like it's an estimation from above, right, of the real Wasserstein distance. What about the Hellinger-Kantorovich one? Is it still an estimate from above? So you have an inequality, or there is some asymptotics? I don't know.
Yeah, exactly. So I mean, okay, so it should be an approximation in a very formal sense. So I mean, there's not very much theory around. I mean, as far as I'm aware, there's no theory around how good this approximation is for the Hellinger-Kantorovich distance. There is some theory around how good this approximation is for the Wasserstein distance. I can't remember the references off the top of my head, but people have kind of looked at this. I think the question is still kind of largely open from my understanding, but there are kind of some bounds here which kind of quantify how close they are. And of course, it depends on how curved the Wasserstein manifold is. Yeah, in terms of like the Hellinger-Kantorovich approximation, yeah, I mean, as far as where, and I'd be surprised if anyone has actually so far has actually managed to kind of quantify this. So I'm not aware of anything. I mean, this is also, I guess, like the distance in the tangent manifold. So this should be a, okay, I have to think now whether it's a lower bound or an upper bound, but it should bound it from one way. I guess it's probably a lower bound, but it's after 5 o'clock here, and I'm too tired to kind of think about which exactly which way it is. But yeah, but in terms of the upper bound, I think there's nothing. Well, at least I know of nothing.
Thanks.
Thank you, Matt, for very, very interesting, inspiring talk. This is really. Is it open? Can you hear me? Okay. Yeah. This possibility of doing principal component analysis in space of distribution is a very, very interesting direction. And I'm been wondering, if I understand correctly, so doing this in the tangent space and having this linearized distance, many things depend on the choice of mu, right? do you optimize on that? Like later on, you showed two principal components. Now it looks like it might be quite critical what choices are made.
Yeah, yes, okay, this is a very good question. So first of all, we haven't really done any proper optimization. I mean, in theory, I guess the optimal sort of mute should be the barycenter. What we actually found in experiments is that it doesn't really seem to matter. We can actually be fairly lazy and just sort of pick almost anything. It seems to work fairly well, which is a little bit surprising. But yeah, I agree. I mean, like in the, if this is my sort of representation of all my points, and if I pick my sort of my cluster center is somehow right over here. Okay, so I guess the center is always going to be at 0, but if I kind of shift this, I would expect the results to be quite bad. But it seems like it doesn't really matter if you just choose, for example, choose the first image to be your center. If you just choose like a Euclidean average. So I think when Diane did this, he didn't use the Wasserstein barycenter, he used like the Euclidean barycenter. And again, that seemed to work sort of quite well. So it seems like maybe the space is fairly flat where you kind of care about it. But this, of course, is just kind of what we empirically observe.
It would be probably a bit more difficult if the space starts being very curved in the neighborhood of the densities that you're looking. Like, for example, if the barycenter is way off from.
Yeah, exactly. Yeah, exactly. I mean, I agree. Yeah. I think as long as you choose a center that's kind of, roughly sensible, you seem to okay. So I mean, actually, I think, yeah. So in our case, we don't even choose something that's particularly that sensible. This is our reference image. It's just a uniform measure over the whole space. And kind of the reason why we sort of do this is, well, it's because we want this condition, exactly this condition here. We want the support of mu to kind of cover everything. Yeah, I guess it's a trade-off between choosing a good center and, if we don't choose a center which spans the whole space, then we kind of lose something in the, we'd have to account for the this term here somehow.
Yeah, thanks. So yeah, in our experience, just to comment briefly, in our experience, the source measure, right, the following features were advantageous, right? That it's at least as smooth as the measures that you're trying to represent, so that it can represent somehow the information they have. I mean, if you took some measure that, I don't know, only has few delta masses, right, to go to extreme, right, then a lot of information is lost, right? And also that, okay, a lot of the measures, with these phases and cells, they had similar support, right? So it also there is this requirement that, or, it's advantageous if the source measure would have similar support, right? Again, that it represents that part of the space, like all of these other measures. But that's just purely empirical again, right?
So I was curious if you wanted to linearize your manifold not only about one measure, but you choose, say, 2, 3, 4 points and represent the data with a logarithm at those points. Do you think that could give you a better representation, that could give you better clustering?
Yeah, it's an interesting point. I mean, I guess this is kind of what we did with the, in this sort of data generating sort of example that I guess the problem you sort of have if you want to do sort of clustering is that how do you compare points on different tangent planes, right? They're not kind of directly applicable. And somehow, I mean, I guess if you want to do clustering, then you've probably already done the clustering to kind of approximate them locally around each point anyway. So yeah, I mean, whether or not one can look at maybe doing this sort of approximating at sort of several different points on the manifold and then comparing, all of these, but this kind of brings us back to the sort of what's a good cluster center problem. And it seems like we're not really very sensitive to the cluster center. So in that sense, I don't think there's probably a huge amount to gain, but with the caveat that, if you're trying to do data generating, it seemed to work a lot better to do this sort of local approximation like we did here.
Thanks, Matt. So it's time for us to move on. So we'll stop here with the questions, but let's thank again, Matt, for this intriguing talk.
Yeah, thank you very much, everyone.